Welcome back to our quantum key distribution series. In this lecture, we take another exciting step forward by exploring fundamental concepts in quantum mechanics that are central to QKD. We'll discuss how unitary transformations govern the evolution of quantum states and introduce the most commonly used quantum gates that form the building blocks of quantum protocols. A pivotal principle in quantum mechanics we will explore why it is impossible to perfectly clone an unknown quantum state, and how this limitation ensures the security of QKD. These ideas are not only theoretically fascinating but also lay the groundwork for understanding the secure communication protocols that QKD offers. So let's start with our first concept, that is the concept of unitary transformation. So we know that there are certain transformations that are allowed for classical bits, like there are bit flip operation and we can add two bits. But there are certain operations that are allowed for qubits, and they are bound and have some limitation due to quantum mechanics. And these operations are called unitary transformation. And these transformations are usually used for modeling some type of transformation for the closed quantum system. So consider we have a state psi in that is given in equation 1, and we apply a unitary transformation on it, and it will transform it to another state, that is the psi out. So the property of the unitary transformation is that it is the both the states, the psi in and psi out, are part of the same uh, Hilbert space of dimension d. So this kind of transformation is usually called unitary transformation, and it follows two general rules and limitations to be physically valid and to be valid to unitary transformation. And the first one is the linear, and it should be linear, and the linearity is shown in equation 2 as the unitary transformation of the whole state is equal to the unitary transformation of its linear combination, and it should preserve the length. And we know that how to calculate the length of this vector by taking the inner product, by taking the self inner product, and we are taking it for the psi out state, and we know that the psi out state could be manipulated by the unitary transformation. And in order to satisfy this equation 3, the unitary transformation should follow this condition that is given in equation 4. That is the complex transpose of the unitary transformation and its multiplication with the normal form of the unitary transformation should give us the identity. So the unitary transformation are time reversal, as we could reverse the effect of the certain transformation by uh, applying the complex transpose of that transformation as given in equation 5. So this property of the unitary transformation is called time reversal. So we could show unitary transformation by equation 6, and it is usually called the Hadamard transform or Hadamard gate. And in order to check that it is a unitary transformation or not, we can take its complex conjugate and can multiply it with its normal form. And if we get its identity, the result, and if we get the result, its identity, so we could be sure that the given transformation is unitary. So in that case, the multiplication with its complex transpose gives us the identity, that is the 2 by 2 matrix of with the diagonal elements of 1 and anti-diagonal elements 0. So this is the valid unitary transformation. So when we apply it to the standard basis, that is 0 and 1, we get the superposed state of 0 and 1 in that case. So when we apply it to the 0 state, we get the plus state, that is the superposed state of the form of 0 plus 1 with the square root 2 factor. 1 over square root 2 factor. Similarly, when we apply it to the one state, it gives us the minus state, and these two possible orthonormal states are the Hadamard basis, and we could suppose the Hadamard transform as changing the standard basis to the Hadamard basis. So both are normalized bases and both are part of the two-dimensional Hilbert space. So it fulfills that fulfills the definition of the unitary transformation, that it transforms the normalized state into another normal state that is part of the same space. So this transformation is called Hadamard based transform or Hadamard gate. So there is another transformation, and it is the general transformation, and it depending upon the theta, and it is given in equation form, in equation 9 of that form. And in order to check again that it is unitary or not, we have to take the complex transpose of it. And it is just taking the complex conjugate of its element and taking the transpose by changing rows into columns and multiplying both to each other. And we get the result identity. So we are sure that the given transformation is unitary. And if we act this transformation on 0 and 1 state, we get the result in given in equation 12. So this is the general form of the state that are uh, uh, in the result of that transformation. So in order to find what kind of transformation it is, we could plug in numbers, that is the theta number, and if we plug in the theta is equal to pi by 2, so we know that the cos theta pi by 4 is 1 over square root 2, and sine pi by 4 is also 1 over square root 2. So in that case, we get the result as for we get in the case of Hadamard basis, Hadamard transform. So uh, this R pi by 2 transformation is not different from the Hadamard transform, and we can say that the Hadamard transform is just a special case of that general transform. So we could build any transform by plugging theta is equal theta to any number and see what kind of transform pops up into our page. So another important transformations for two-dimensional Hilbert space are Pauli matrices, and they are X, Z, and Y. And these we can also interpret them as the gates in quantum computing. So uh, X and Z usually uh, acts as the bit flip and phase flip operators. So in equation 15, we can see that when it acts on the standard basis, that the X operation acts on the standard basis, it acts as a bit flip operation, as it interchanges 0 into 1 and 1 into 0. And similarly, the Z basis, the Z operation does not flip any kind of bit, but it changes the phase of the original bit. So when it acts on the 0 state, it does not change the phase of that state, but when it acts on the 1 state, it changes the state of that state 1. So we can say that the X operation acts as a bit flip operation in standard basis, and Z operator acts as a phase flip operator in the standard basis. Similarly, uh, their roles flips for the case of the Hadamard basis, as Z operator acts as a bit flip operator in the case of the Hadamard basis, and the X operator acts as a phase flip operator in case of Hadamard patches. So why operator acts as a bit flip and phase flip operator simultaneously, and it has property of both the operators as it is composed of the X and Z operator. So we could see that in equation 19 that when it acts on a zero state, it gives us a state 1, that is the bit flip operation, and the phase it changes into an imaginary number, that is the I iota. Similarly, when the Y operator acts on 1, it flips the original state into 0 and gives us the overall phase -1, minus iota. So that's how these operators work in the form of the standard basis and Hadamard basis. And similarly, results could be inferred by acting Y operator on the plus S minus basis, that is the Hadamard basis. So the next concept is very important as far as we are concerned with the security of our protocol. So this is the no cloning theorem. So we know that the original classical bits could be copied without any restriction and limitation, but in quantum mechanics there is a restriction in copying of the qubit. So no cloning theorem states that there is no unitary transformation that could copy the unknown state without disturbing it. So there is a inherent difference between the copying of the classical bit and the qubit due to the condition imposed by the unitary condition imposed on the unitary operator by quantum mechanics. That is the linearity and uh, the length preserving property of the unitary operations. So in order to prove this claim, we can assume that we have a copying operator and we denote it with C, and it acts on the unknown state. Let's say it's psi, and it gives us the copy of that state. So consider we have state psi1 and psi2, and it acts on psi1, it gives us the copy of psi1, and when it acts on psi2, it gives us the copy of psi2. So unitary, it is a unitary transformation, so it should follow the condition of the unitary transformation, that is the multiplication of the complex transpose of that transformation with its normal form should gives us the identity. So in order to calculate the inner product of that states of these states, that is the psi1 and psi2, we could write it in that form. So we could introduce the inner product of the 0 and 0 state, that is the self inner product, without losing any generality, as the inner product, so the self product should be 1 is equal to 1. So separating the bras and cats, we could write it in that form, and we know that the product of the complex transpose of the unity transformation with its normal form should be equal to identity. So we could introduce it in between these parentheses without using any generality. And we know that when it acts, that complex transpose transformation acts on the bras of inside the parentheses, it gives us the copy of that state, that is the copy of the psi1 state. And when this unitary transformation acts on the psi2 state, it gives us the copy of the psi2 state. So using uh, this bras and cats into parentheses, we could make the inner product with the corresponding bra and cat. So we get that form, and it is just not, it is just a modulus square of that inner product. So we know that when in the case of the psi1 and psi2 are not equal and they are different to each other, their inner product should lie between 0 and 1, and it should not be equal to 1. In that case, they should uh, be equal to each other, but we have assumed that they are not. So the inner product should lie between 0 and 1, that is less than 1. So we know that for any number that is less than 1, its square should not is not equal to uh, the original number. So the inner product, that is the two numbers, should not be equal to each other. So this negates all our whole process and our whole assumption uh, of the copying unity transformation. So, uh, due to the property of linearity of quantum mechanics and the unity transformation, that kind of operator does not exist, and that's how we cannot copy any state that is the qubit that is unknown state and without disturbing it. So this is the no-cloning theorem, and it plays very important and crucial role in QKD protocols. So consider we have state that is the superposed state of 0 and 1. And in order to uh, copy that state, uh, we have to determine the complex amplitude of the complex amplitude of the uh, corresponding state, that is the 0 and 1. But we cannot measure them because uh, in order to measure them, we could measure them, but we cannot copy the state that is the superposed state of 0 and 1 without disturbing it. So when we measure it, it would collapse into one of the case, that is the 0 and 1. So uh, it is impossible to copy this state in one go. So, in some sense, the qubits are precious, and we cannot determine the state of an unknown qubit by without measuring it and disturbing it. But measuring it to disturb the state, and it would collapse one of the state, that is the state of 0 or 1. So that is the fundamental difference between copying the classical bit and the qubits. So this makes the whole process very secure, and no-cloning theorem no-cloning theorem lays a foundation of many QKD protocols. So let's summarize what we have covered in today's lecture. We explored the concept of unity transformations, which govern the evolution of quantum states, and introduced key quantum gates that play a critical role in quantum computing and QKD protocols. We discussed the no cloning theorem, understanding why it is impossible to clone an unknown quantum states, and how this fundamental principle ensures the security of quantum communication. These concepts form the backbone of quantum cryptography, making QKD a robust and secure communication method. Thank you for joining this session. In the next lecture, we will dive deeper into some another concepts of and aspects of the QKD protocols. Don't forget to like, share, and subscribe to stay updated. See you next time.